So we're going to start talking today about our last little section here called relative velocities. So this is basically when you make your frame of reference just a little bit different. Okay, so maybe you are sitting on a moving object and something drives past you, or maybe you are the examples that your book and a lot of physics problems like to use is, let's say you're trying to swim across a creek that has a current, right? So that current is pushing you downstream a little bit. So we're both kind of finding velocities. We're going to see what that final overall velocity is if you're trying to swim and that creek's pushing you downstream a little bit. That's an example that we like to use a lot. We like to use wind currents a lot. So let's say I'm flying a kite, or if I'm flying a plane or something and a wind current is pushing me. Those are the types of things that we're looking at with relative velocities. Okay? So for example, if we've got two trains that are traveling 80 kilometers per hour toward each other. Okay, so visualize what's happening here. You don't necessarily have to write this part down. Okay, that's up to you, but let's just visualize what's happening here. And you happen to be standing on standing beside the tracks. Okay, not on the tracks, hopefully, beside the tracks, and you can see these two trains. Okay, you standing still would be able to see that both of those are traveling at equal speeds. Right? If you could calculate in your brain or visualize 80 kilometers per hour, you should be able to see that they're each traveling with their own individual velocities, and they happen to be at the same speed toward each other. Can you visualize that? Okay. Now let's say I'm standing on one of the trains. Okay, so if I'm standing on one of the trains, my train's moving 80 kilometers per hour, the train coming toward me is moving 80 kilometers per hour. It would seem to me as if that train coming toward me is moving twice as fast, right? Because I'm moving, they're moving toward me. We're closing in on that gap 2 times as fast as if I was just riding on the train and there was nothing coming at me. Okay, so that frame of reference is what I'm talking about here with relative velocities. Things change a little bit depending on where you're viewing this from, or depending on what two velocities are kind of colliding here. Okay, so let's just think about this question. If I'm going 70 on the interstate and I come up on a car that's going 55, does it feel to me like they're traveling 55 miles an hour, or does it feel to me like they're traveling faster or slower than that? It feels like they're traveling really slow, right? Maybe 15 miles an hour. The difference between those two. Does that make sense? This is what I want you to think of in terms of relative velocity. Just like if you're driving down the interstate and you can see someone in your rearview mirror that's driving the same speed as you, it doesn't really even look like either of you are moving, right? Because you're both traveling the same speed. You're not closing in on a distance. You're not pulling away from that car behind you. So that relative velocity is when we were comparing basically these two velocities with each other. Okay? So you come up on a car that's traveling 55, it feels like they are barely moving, right? When realistically, if you're standing on the side of the road, it's going to look like they're going really fast. Okay? But if they're traveling with your frame of reference at 70 miles per hour, it doesn't seem like they're moving very fast at all. Okay? Does that make sense? Okay. So those examples that I just gave you with the train and with the car, those are examples of same line velocity, which means we're not dealing in 2 dimensions yet. These two cars are going in the same direction, okay, or at least on the same axes. Right? They're both traveling north, or one's traveling north and traveling south. We're on that same line. We're not having to deal with angles yet, or perpendicular kind of intersections yet. Okay, so we would just use simple addition or subtraction to solve for those same line velocities. If one item is moving north and one item is moving south, we would subtract those two, right? If we're going in the same direction, we would add them. If we're not in the same line, we're going to use vector addition. So adding our components, finding our resultant vector, just like we've been doing the last couple days, okay, to find the velocity of one object with relation to the other. So relative velocity gets into a little bit tricky diagrams. And when I say tricky diagrams, I mean you picking out what the resultant vector is a little bit trickier with these problems, just with the way that they're worded. And your book, I don't think, does a great job with this. They try to put lots of subscripts with each of our vectors, and I think it's a little bit more confusing than it needs to be. So I'm going to give you a little bit more of a simplistic bare bones kind of version that I think is more applicable for when you're drawing these diagrams, rather than to try to walk you through what the book is doing. So it's important for you to draw the diagram here and see what your resultant vector is. So remind me what your resultant vector should be telling you. Yep, final displacement, or it's telling us where we're ending up as compared to where we started. So our resultant should always go from our origin to our ending point, where we want to end up. Okay, that's really important for these diagrams. And I'll show you some examples of that here in a second. But your resultant and drawing the resultant is really important. When I add my vectors tail to tip, they should always end up at the tip of the resultant as well. Okay, so you might draw these diagrams out of order. You might draw your resultant first, then draw your vectors to add to your resultant. Okay, that kind of makes sense? Hopefully as we go through some examples, you'll see what I'm talking about here. Okay, so here, this tells us a boat needs to travel straight across a river that has a current flowing at 1.2 meters per second west. They leave the shore with 1.85 meters per second. What's the actual velocity of the boat? With what angle from the shore must the boat be traveling to achieve the goal of ending up straight across the river? Okay, so this is kind of a wordy problem. So write down what you need, and we'll start talking through what we're actually looking at here. I have the velocity of the water, which is going 1.2 meters per second west, right? The boat says it's leaving at a velocity of 1.85 meters per second. But its goal is to end up straight across from where it started. So here is my origin. My goal is to end up straight across from where I started. So that has to be my resultant vector. Okay? If I know the current is pushing me west, that means I need to add tail to tip to that resultant, right? So I want my resultant always to go from my origin to the tip of my last vector. So I have to make that basically tip to tip of those vectors. So to get there, I have to leave in this direction. If the current's going to push me west, I have to visualize in my head, okay, I need to leave this way if I know the current's going to push me west and I want to end up straight across from where I started. Okay, so when you do these diagrams and you do these relative velocity problems, you really have to take a step back and think, okay, what's my overall goal here? Where is this going to push me? Where should I end up here? And that's going to tell you what direction you should leave with. Okay, so if we know we're leaving with 1.85 meters per second, our current is going to push us 1.2. What's the actual velocity here of my boat? Right? I'm going to fight the current. I'm going to go out against the current here in order to end up straight across from where I started. Should our velocity of our actual boat be greater than or less than 1.85 meters per second? Less than, right? It can't be greater than the hypotenuse of our triangle. Okay, so it should be less than. So this is a squared plus b squared equals c squared. You're just using Pythagorean theorem here to find that. And the subscripts here would be an example of what your book does. And all this is meaning is this is the velocity of the boat relative to the shore. This is the velocity of the boat relative to the water. Okay, so I'm leaving in the water 1.85 meters per second, but if I was standing on the shore, this would be the actual velocity that I'm seeing here. Okay, so Makara, what'd you get? Kelsey, do you have it? 1.42. What's our units? Meters per second. Okay, and what angle? Does anyone have the angle ready for me? Tell me one more time. 40.6. 40.6 degrees blank of blank. What is it here? Good. East of north. Same river example, same boat. Now he just leaves straight across. Okay, he just leaves going straight out from where he started, or where he started on the shore. The current now is going to push him this direction. Right? So if you just leave heading straight, that current's going to end up pushing you downstream a little bit more. So our resultant here is going to tell us that we're going to end up somewhere downstream west of where we started. Do we agree with that? Okay, so I know these diagrams are already drawn for you. Hopefully you can see what would be happening if we were doing that on our own, right? We're going to leave straight out from where we started. The current is going to push us that way. That means our resultant should end up somewhere to the west, right, and downstream from where we started. Okay, so now our 1.85 meters per second goes with our northerly vector. Our current is still moving 1.2 meters per second. So now what type of velocity could we be expecting? Greater than or less than 1.85? Greater than. So now the current is working with us, right? The first time we left against the current, it's going to slow us down a little bit. Now we're going and the current's going to push us along. So we should be moving a little bit faster. Okay? So solve for the hypotenuse and give me that angle as well. All right, Keenan, what do you have for your just the magnitude of the velocity? 2.2 meters per second. Good. Alicia, do you have the angle for me? 82.6 degrees. Not what we got. Okay. Wait, was it 2.2? Okay. And then what was the angle? 32.9. Probably just a calculator thing.
Did you take like
West of north. Good. Okay, west of north. Very good.